Okay. Hello, everybody. I'm not a tensor code user, so I can just only talk about what I did in the past. So I spent some time studying spiral gases and lengthy wave. So today I'm going to talk about fueling mechanism in the bulk gas. And this is my former advisor on my master's thesis. What we are interested in this is because recent development in observations showing a lot of circumnuclear activities in active galaxies. Two very prominent phenomena is starburst and AGN, and they all need a lot of gas fueling into the central kiloparsec region to produce such burst behavior. So we are interested in how this can be done. This gas fueling can be done. So now, in general public believe there are two main mechanisms to produce this gas fueling into the circumnuclear region. One is a bar structure, and the other is a gas-gas interaction. In this case, you see in this bar galaxy that it has a common two-grain design, a spiral arm. But if you look into, this is an active galaxy, and if you look inside the circumnuclear region, you can see very clear dust layer and young stars going into the center. This is a clear evidence that showing there are something going into the center to produce star formations and the central activity. And in the galaxy interaction, this is the example of M82 and M81, and this is another galaxy. In the optical image, these three are actually isolated. You don't see any connections between these three galaxies. But if you go into the CO or H1, you will not CO, H1, this is H1. You will see a lot of tidal bridges connecting these three. So that is an evidence that actually these three are actually interacting with each other. And fueling gas inside, I believe, is this one, M82, this is starburst gas, to produce the previous starburst HST picture you saw. But today I'm going to only focus on bar gas, how bar can fuel the central activity. Another interesting phenomenon observed is that there are many circumnuclear rings in a spiral galaxy. These are three examples, and this is a bar galaxy and with a nuclear ring. But if you use HST to observe the central region, you can see actually it's composed two arm spirals. So spiral feature can also produce a ring structure, like a ring-like structure. But here, these two galaxies show very circular rings. So it's maybe possible that, and another feature is a very straight dust lane. So it's possible for gas to filling in and deposit it on a certain radius and to produce a starburst ring. But the question is, what determines the size of this radius? So there are several questions to address to these observations. So our approach is first to use analytical solutions to see what the spiral structure and gas streaming motions looks like. And my former advisor practically spent many decades, a lot of decades, to try to formulate using a syntactic method to formulate from the fluid equations into a simple quaternary differential equations. And this is the nonlinear syntactic theory. our model is basically a gaseous disk driven by a rotating bar potential. And the disk is uniform, isothermal, viscous, self-correcting, and rotating differentially. And the basic assumptions we put in is a quasi-steady in a co-rotating frame with the bar. So the pattern is unchanged. And the other is a famous type 1 approximation. And use these assumptions, the partial differential fluid equations can be reduced into complex second-order ordinary differential equation. And you can just simply solve these ordinary differential equations much quicker than directly numerical simulation to the PDE. You can find a quasi-steady pattern, including kinematics, of the spiral structure. So that's the strength, advantage point of using this approach. If you're interested, you can talk to me, and there are lots of references to these two papers. So what's the prediction of this theory? That it can generate 3 different characteristic spiral patterns in different resonance excitations. ILR means inner linear resonance excitation. That means it's inside the co-rotation radius. OLR is outer linear resonance, is resonance excited outside the co-rotation radius. And there may exist 2 inner resonance. We can additionally differentiate between outer and inner linear resonances. And using this theory, you can produce 3 different structures. First is both OLR and OILR produce trailing spiral arms, and IILR can produce a leading spiral structure. But these are not really observed because it exists at the very center of the galaxy. So if this structure can exist is still questionable. But in the theory, it is predicted it can be generated. Also in the simulation, actually.
You missed maybe one thing. What about this Q parameter? How is that varying through the disk?
Q parameter?
The tumor instability parameter. Isn't that a critical thing here or not? Or is it just a pattern? No, it's not circle-sided, it's spiral.
You're talking about tumor instability here? I think in the formulation we assume it's stable disk, not unstable disk.
And actually, the other thing, are you talking about only the stars and not the dust?
This is a gas.
That's
gas
only dust, is the gas? And
only
what about
gas.
the stars?
Stars only go into the gravity passively.
So they determine the gravity field mainly?
Right.
Mm.
Only determine the field.
Okay, then Q of course is only relevant to the stars. Not to
Mostly,
yeah.
yeah. Gas can partially contribute, but very small.
And so the stellar composition is the same in all these 3 different cases?
Yes. You can actually generate 3 resonances simultaneously. One is inside each other. This is inside here, this is inside this one. But the problem is that there is no such large extent galaxy existing. So it's very hard for multiple resonances coexist. But it's possible. It's possible. Okay, so the characteristic feature is these 2 are trailing, this is leading, and about pitch angle, this is type 1, this is 1, this is very open, and this is also very open. And from the kinematical information, we also know that this is driving the gas outward, these are driving gas inward. About this is possible in both ways, but mostly inward. Okay, so what interested us here is this one. We want the gas to fill into the center. So we think most of the activity is generated by this excitation. So this is the sample case we studied, real galaxy. What's special about this galaxy? It has a very, very extensive data available. And you can see it has a very large dynamical range. A 2-arm spiral goes all the way to the center. So this is a case study for us to compare our theory to observations. And actually, we have successfully matched the two by just supercomposing. So, and this is the central region. CO observation with line of sight velocity. And this is our kinematical data with the line of sight velocity contours. And the basic feature is that the contours is bending outward along the spiral arms on top of the spiral pattern of the differentially rotating disk. And this feature is also observed here. So both kinematically and morphologically, we match the two. So we have the confidence of our parameters that can predict in this galaxy. Okay, so enough about the theory. But remember the basic assumption is the quasi-steady frame we used. So we still want to use numerical simulations to confirm that this can exist. So that's the second part. And I think it's most relevant to this meeting. I wrote myself a hydrodynamical code trying to simulate gaseous disk using Randy Lafayette's wave propagation method. I believe more or less everybody knows about his book. I'm very proud of it. It's a good enough scheme achieved to the second order. And what makes his method different from other good methods is that it's the directionally unsplit. And this method has a second order transverse flux corrections to correct for the cross terms. So these are two distinctive features of his method from other people's doing. I use the 1024 square uniform Cartesian grid. And isothermal equation state, and I solve the Riemann problems exactly. Use the mean mass velocimeter. I put no cell gravity into this system because in the previous prediction, we found that self-gravity should be very small effect. So basically, I put no cell gravity into the system. And the source terms are axisymmetric potential to supporting a differentially rotating disk. And I use the rotation curve as the previous case study. And I use the external rotating bar potential into the system. And here is the result. Now, although I solved the system in inertial frame, here is the rotating frame animation. Bar is always in horizontal position. And this is the log density profile. And it takes about 300 million years for bar to rotating once. You will see the bar rotating 4 revolutions. And you can see it generates very nice 2-arm spiral structures. And very quickly evolve from one state to another state. Now, separate the different snapshots. 1 revolution, 2 revolutions, 3 revolutions, and 4 revolutions. Only the first frame is similar to our theory predictions. So this has drawn us the conclusion that the time scale for our quasi-steady assumption is very, very short. The system quickly evolved into another state because of a very, very huge gas inward streaming motions. But basically, the gas is cleared out at the resonance region and into another state. And also you can see there's a feature here. And looks like there's an accumulation around here. So this is a sign showing that there are different filling rates at different radius. So if you, this is a azimuthal profile at a different radius. I just want to show you how good it captures the shock structure. And also another thing is that at the round radius, the resonance is at 3 kiloparsec. And around the resonance radius, strong shock is produced. And if you go to the central region, for example, less than 2 kiloparsecs, the spiral waves becomes very linear. So from very nonlinear to linear region is also another distinct feature of this system. And this is a density average density, azimuthally average density with radius. And here are different times. You can see the gas is cleared and accumulated into the center at around this radius. And there's a small filling diffusion still occurring inside this radius.
And excuse me, what's your initial condition in these simulations you just showed? Do you have some white noise in there?
White noise?
Is it some random fluctuation?
No. It's
There must be
uniform.
something, right?
I'm sorry?
Because it was exactly, can you go back? It was exactly symmetric. I mean, no, on the next page. It's completely symmetric. I mean, it was. Have you tried breaking that symmetry?
Breaking. Break the symmetry. No?
I don't know why I should break the symmetry.
Either that or just calculate half of the disk.
I can't calculate the full disk.
Yes.
Why do you do that if you have complete symmetry?
Oh. Because it's cheap, so I don't need to. It's 2D
But it
calculation.
might be interesting to break it, no? Maybe just to see how stable it is and whether you...
We are not interested in stability in this system. We just want to compare the numeric simulation with the theoretical prediction.
But on the other hand, if it's time evolving and the other mode was indeed excited, was at least initialized, then of course, if it was excited and it was growing faster, you would actually see other modes.
Yes,
That's
right.
Now, in this case, you cannot really be sure because the conditions, the solution is just perfectly symmetric. So it's possible that the initial condition never had any departure from this m equals 2 structure.
Yeah.
That's what he's saying.
Yeah.
And then it will never be generated, even through numerical noise or machine noise. There's no way of producing that.
Right.
But every noise will have also the symmetry property.
Yeah.
No.
I know it's...
What's your last point?
Hmm?
What's your last point? No.
That the machine is the
The arrows are symmetric as well, yeah?
Yes.
I mean,
if everything is symmetric with respect to the mesh, there's no way that there can be any production of asymmetry. Therefore, you were asking if the initial condition was white noise.
There's no noise.
Yeah, but why not? Because that would immediately break the symmetry. And it would be a much more general initial condition. Therefore, but if you're saying the initial condition was a uniform one, is that even possible? Is that a solution of the equations? And if so, then of course it may never go unstable, even short, if there was a perturbation.
I don't know, it just... Just to
Actually, if there is no m equals 2 perturbations, that's the external bar potential. If you just want to support differentially rotating disk uniformly or with a pressure gradient, actually it's very hard in Cartesian grid. I've tested this, but we tried very hard to minimize the deformation of the disk from the uniform. So we don't actually want noise inside of this. And we just want to see how m equals 2 perturbations can have on this system. But it may be interesting to put noise inside of it here to see what happens.
I think so, yeah.
Yeah. We just want to match the two different methods, the results of two different methods.
You mean just because let's say you put in white noise now, and then something completely different happens. Then then the system actually develops additional structure, and after a few revisions, what would that actually tell you? I mean, that would be pretty.
If there's some distinction,
because that would never happen in nature, right? You don't have perfect symmetry.
That's true. That's true.
I mean,
That's true. That's true. Okay, so to demonstrate the gas streaming motions along these spiral structures, this is the streamline plot, and you can see that basically the gas encountered a strong spiral shock, and spiral shock focus the gas trajectories into the subnuclear regions. But remember that inside about one or 2 kiloparsecs, the wave becomes more or less linear. Then this focusing effect becomes less important, and it goes back to usual linear solutions with overall distortions in their circular motion. So this is the why there are different inward fueling rate from outside to inside. So we try to connect all the pictures together. First, the spiral structure is actually determined by the kinematics of the differential rotation of the disk, and the rotation curve at different it's just like the natural frequency of this system, and it can determine the pitch angle as a function of a radius. And that can be linearly. You would think you just use linear dispersion relation to predict the pitch angles, but actually it fails, especially in such system. But using the improved theory, you can basically recover the pitch angle function in this system, and then pitch angle decide the shock strength of the spiral arms. If you have a large pitch angle, the gas motion to the spiral shock is steeper. No, it's more or less perpendicular. Then more shock strength can be produced, and more focusing effect can be produced to make the largest inward streaming motions. So these are shock strengths at different radius. So you can see general trend in pitch angle and shock strength. And here is the mass fueling rate at different radius. Here is the enclosed by 1.5 radius, and you can see a lot of this is mass, enclosed mass. This is the fueling rate. A lot of mass is driven in a very short time from outside 1.5 kiloparsec into the 1.5 kiloparsec. But if you go into 0.15 kiloparsecs, it's not the burst behavior, but a very small fueling rate, slowly diffusing at the very center. So that also matches the previous slide that how to produce burst behavior just from the spiral structure. And here is the 50-48 case that it shows starburst rings may related with this idea. So there are just several conclusions that we think the bar-driven system, by producing outer inner limb resonance excitation, gas can be driven into the very center. And how to diagnose this streaming flow just by you can just use the kinematical information to determine this. And there are several correlations can be identified. One is open spiral structure can produce stroke shock and produce large filling rate and produce burst behavior. A tightly wound spiral just give you a weak shock or linear wave, and then filling rate will be very small and continuous accretions will occur. So this is basically the picture. I think that's it. Thank you. Yes.
How far into the spirals go? In other words,
You mean observationally or this simulation?
I saw that last picture you had, picture.
Yes.
And there's a second sort of ring.
Right.
Here, but that's still on order 300 parsecs across.
Even smaller than that.
Yeah, and how far? Observation, do you know how far down they go? If you get structured nuclear rings that
this
are
is the
parsecs away.
This is the end point of their identified spiral structure.
So the ring that's
But
inside
it does not mean the spiral structure doesn't go even more because of resolution.
That's as much as anybody's going to claim.
Yeah, so they basically just identify to this point. This is around 1 kilopascal. I think, no, 300 to 400 pascals. And simulation, you can generate all the way to the center.
How strong? I guess how vigorous are the formation of the bars relative to the strength of the AGN at the center? Generally, I mean, just order of magnitude. Like, if you have a stronger AGN or louder AGN, do you have more bars being formed or bigger bars being formed, or?
I think it is down the other way around.
Oh,
You should first have the bar
bars
and
being
then
formed
generate
AGN.
to trigger AGN.
Hmm.
And there are a lot of people studying how unstable can generate bar structure, because that's a different issue.
Now, how about magnetic fields modifying the gas flow? Because magnetic fields are in competition with the gas.
Yes, true. I believe in galaxy disk, magnetic field can modify structure less than kilopascal scale. So we can only claim that our structure is in and above kilopascal scale is true.
But the structures are sharp. They have thickness is much smaller than kilopascs. They're sharps.
Yeah. So that's right. That's the limitation of this depiction.
They were modified by magnetic fields.
Yes, in small scale.
And may then affect the way how you fuel your gas further inwards.
Yes, that's right. So
I mean, there's
at some point it must be added in.
They also put a similar paper by Shukurov and Moss and others who investigated the effects of magnetic field from dynamo models on the gas flows, and I think they were. I mean, in one of the galaxies, I think they also observed that there was some systematic phase shift between the location where the magnetic field actually shocks, which does show a shock, and where the velocity field shows its shock. Mm-hmm. And they were able to interpret this in terms of magnetically driven shock. So it sounds, from that point of view, critical to include that.
Yeah.
But your plans with the pencil cord, are they related to this or
No.
not?
I'm just basically follows Andrew's work, and we want to study particle behaviors in cancer.
So it's kind of a hybrid of Jeff's work and my work. So combining the dead zone with the sedimentation of salt and the salt levels. And then we want to use this probably this non-equidistant grid also. But that you're using that then? Because when we have to have dead zone, we have to have a lot of scale height, so then modeling this tiny midplane might be difficult. We've got to try to get higher resolution in the midplane. So hopefully that will work.
Yeah.
What's your experience with that?
Is it non-good? I think it was implemented correctly, so it should work.
How does that work with the viscosity? Does it assume the same viscosity or does it make less viscosity?
Some second derivatives are okay. Hydro, I'm not sure. Are you using hydro viscosity?
No, that's it.
That may not be it. I'm not sure.
That would have to be adapted.
It may by the way work actually. Because all we do is we do it. Maybe it doesn't work.
We need to have lower viscosity coefficient where the resolution is high.
I don't think you want to change for the hyper diffusion. You want to change the coefficient. You basically, I see hyper diffusion as something that doesn't care about the grid positions. It's just something you apply, some smoothing you apply depending on the values in the neighboring points. That where those points are, you don't care much about.
No, but it depends on delta x to the 6th power, right?
No, but he's saying he wants to take that out.
There is some.
Yes,
It
makes sense.
the coefficient scales with delta x to some power.
Yes.
But
And the upwind expression.
The hydro coefficient as well.
And also the coefficient for the high viscosity.
Oh, you're talking about taking the delta x's out, just like with the shock viscosity.
the if you how does that work? I think there might be some overall scaling with some characteristic delta x.
Of course.
Yeah, delta x to the 5th.
But other than that, I wouldn't care. So basically, you can map your grid to a uniform grid with a representative value of delta x, and there you apply standard constant coefficient hyper diffusion, and that's not the way you code it probably, or to some extent I guess
It would have to be recoded that way.
Well, it's closer to what we have now than if you were to take into account the varying delta x. It's just that you need to make sure you're not actually using that quantity that now is an array and thing. More questions? That's not the case. Then let's thank you again.